The LU factorization is a method of factoring a matrix as a product of two matrices and using it to solve a system of equations in a manner that is perhaps slightly more efficient than performing row operations to their fullest. So we're going to need to recall a few definitions. First, an upper triangular matrix is one whose entries below the main diagonal are 0. Here's an example of an upper triangular matrix, U, which has entries 2, 6, 0, 1. You'll have to forgive the green rectangle, which is trying to focus. A lower triangular matrix is one for which the entries above the main diagonal are 0. Here's an example of a lower triangular matrix. And such a matrix is said to be a unit lower triangular matrix if all the diagonal entries are equal to 1, and that is certainly the case. It's not too hard to show that the product of two unit lower triangular matrices is also unit triangular, and the inverse of an invertible unit triangular matrix is itself a unit triangular matrix. So we can use lower and upper triangular matrices to efficiently solve systems of equations. Let's say we have a vector vector B, which is 1, 1, and we wish to solve the system of equations Ly equals B. So let's write down the augmented matrix. Here's Y1, here's Y2, 1, 0, 2, 1, 1, 1. That's a 1 right there. Now, one means of doing it is to perform some elementary row operations, but we don't really need to do that because this is unit lower triangular. Notice how if we start at the top row tells me simply that y1 is equal to 1. And the bottom row says that 2y1 plus y2 is equal to 1, which therefore is going to tell us that y2 is negative 1. So in other words, y is the vector 1, negative 1. Okay, so if we have a lower unit triangular matrix, we really don't need to perform elementary row operations because we can start at the top and work our way down. And this method is known as forward substitution. Now we're going to do something analogous. I mean, if there's a forward substitution, there's probably a backwards. And that's where the upper triangular matrix comes in. What we're going to do is we're going to take this upper triangular matrix and we're going to solve the matrix equation ux equals y, where y is this vector right here. We're not going to be using b in this case. So let's take u, which is 2, 6, 0, 1. Let's augment it with that y that we got above. Now, if we start at the bottom, we can see that x2 has to be negative 1. And we can also look at the top row, which says that 2x1 plus 6x2 equals 1. And if we use that, x1 is equal to 7 halves. I'll let you check that on your own. So that means the solution vector equals 7 halves minus 1. So this is the method of backward substitution. You'll note that on this page, for the unit lower and for the upper triangular, I simply wrote down a few simple equations. I didn't actually have to perform elementary row operations. Now, suppose I told you that the matrix A, which is 2, 6, 4, 13, suppose that I told you that it factors as L times U. And suppose we wanted to solve the system AX equals B, where B is that 1, 1 on the previous page. We've really done it already, using the associative property. If A factors as LU, we can replace A with LU here. And matrix multiplication is associative, so I can rearrange my parentheses and I have L times UX. But we showed on the previous page that UX is Y, and we also showed on the previous page that LY is equal to B. So we, in essence, have solved the matrix equation AX equals B using the matrix factorization L and U together with forwards and backwards substitution. But wait, it gets even better. Suppose we wanted to solve a new matrix equation, AX equals B, where now B was the vector 3, 2. A is still the same. We don't need to compute a new L and U. We don't even know how yet. We don't need to perform elementary row operations. We can simply peel off the layer, so to speak, and use forwards and backwards substitution, just like we did on the previous page. So Ly equals B. It's the same L as before. The only thing that's different is that the B is now 3, 2. I'll let you check that Y1 is equal to 3, and Y2 is equal to, let's see, Y2 is equal to -4. Okay, 2y1 plus y2 has to equal 2. So that means the vector y is 3, 4. Now let's go down and use the upper triangular, ux equals y. We're peeling off the next layer, so to speak. So let's write u, which is still the same. It was 3, 6, 0, 1. Here's x1, here's x2. Now I'm going to put not b, but this 3, 4 that we computed above. And if we do that, I'll let you check on your own that x2 is 4. Wait a second. This should be a -4. That should be a -4. So x2 is -4. And you can check that x1 equals 27 halves. So that means that the solution vector in this case, using a different b, is 3, 2. So the solution is x equals 27 halves, -4. So the idea is that if we can somehow take a matrix A and factor it as the product of an upper triangular U and a lower unit triangular L, once we have that factorization, we could solve AX equals B using many different choices of B in simple forwards and backwards substitution. And the same idea would actually hold for larger matrices. However, if we have a larger matrices, more elementary row operations are typically going to be needed. The primary question then is, how do we compute the LU factorization of a square matrix A? And the key idea involves elementary matrices. You'll recall that an elementary matrix is a matrix with the property that it's obtained by applying one elementary row operation to the identity matrix. Every elementary matrix is invertible, and the way we get the inverse of an elementary matrix is we apply the inverse operation to the identity matrix. For example, if the original row operation consists of adding twice row 1 to row 2, the inverse operation involves subtracting twice row 1 from row 2, I believe there. Okay? So, the easiest way to row reduce a matrix to an upper triangular would be involving adding multiples of one row to all the rows below it. Adding multiples of row 1 to the rows below it, multiples of row 2 to the rows below it, multiples of row 3 to the rows below it, and so on and so forth. Now let's suppose that would require k operations. Each of those operations can be represented as an elementary matrix. So this would correspond to the first row operation, the second row operation, all the way up to the kth operation. If we multiply those times A, we would get an upper triangular matrix U. So that gives us U. Now we want to figure out what L is, because we want to write LU equals A. And the simplest way to do that would be to multiply in the right order by the inverses of all of these elementary matrices. We know that they're all invertible, and solve that for A. And the way we can do that is we can very carefully multiply the left side by the inverse of E sub k, then the result of that on the left by E sub k minus 1 inverse, and so on and so forth, the last one being E1 inverse. So A is this product here times U. Now what we're going to do is we're going to just slip a little identity matrix in here, just for kicks. So this much, that's going to be our L right there. So if we define L to be this matrix, A is equal to LU. Furthermore, since each elementary matrix is invertible, the product is, so L is invertible as well. Okay? Now, how do we do this in practice? We list the row operations that reduce A to the upper triangular matrix U. Each of these corresponds to a row operation. The row operations that take us from A to U. And then we apply those inverse operations, but in the reverse order, to the identity matrix, and that's what gives us L. Okay? So let's take a look at an example. Let's look at an example where we actually have a larger size matrix. The matrix whose entries are 2, negative 1, 2, 4, 1, 5, negative 2, negative 8, negative 4. Okay, so maybe this is a negative 2, negative 8, negative 4. Maybe that's not easier to see. Okay, so I'm going to write this matrix down so maybe you can see it a little bit easier. It's 2, negative 1, 2, 4, 1, 5, negative 2, negative 8, negative 4. Now, the way I've designed the matrix, it's going to be pretty easy to row reduce this to an upper triangular matrix. What I will do is I am simply going to write the 3 elementary row operations that are required to do this. We're going to take minus 2, row 1, plus row 2, and we're going to place that into row 2. We will also be taking R1 plus R3, and we will be placing that into R3. We will be taking 3R2 plus R3, and we will be placing that into R3. Those are the 3 operations that will take this matrix and give us an upper triangular matrix, which I will be writing down now. This is the upper triangular matrix you get. It's going to be 2, negative 1, 2, 0, 3, 1, 0, 0, 1. So you may want to check actually that these 3 elementary row operations in this order gives us this upper triangular matrix U. Now what we have to do is we have to write down the inverse operations of each of these. Now here's one way I like to think about it. What's the inverse row operation of this? Kind of reverse the arrow here. So instead of going from left to right, it goes from right to left. And then add R1 to the other side. So what we get for the first inverse operation is R2 plus 2R1 goes to R2 if we apply that reasoning. But wait, because we want to apply the elementary row operations in the reverse order. So let's start down here. Let's replace this arrow going from left to right, right to left. Let's subtract 3R2 from that side. So the first inverse operation would be to take R3, subtract 3R2, and put that in R3. That's the first inverse operation. And we're going to do that. We're going to apply that operation to the identity matrix. And if we do so, what we would get is 1, 0, 0, 0, 1, 0, 0, negative 3, 1. So that's the inverse operation of the third operation above. Now we have to get the inverse operation corresponding to this. Well, again, let's think about the arrow going from not left to right, but right to left. We could say that R3 minus R1 goes to R3. R3 minus R1 goes to R3. And we're going to apply that to this matrix. That will give us 1, 0, 0, 0, 1, 0, minus 1, minus 3, 1. The last row operation would be the reverse operation of this, which would be R2 plus 2R1 goes to R2. That's going to give us this matrix. Whoopsie, sorry. 1, 0, 0, 2, 1, 0, negative 1, negative 3, 1. This is our unit lower triangular matrix. This is L. And we could check this by taking L times U and showing it equals the original matrix A up here. So again, there were 3 row operations that took us from A to an upper triangular matrix, and we had to figure out the inverse operations and apply them in succession to the identity matrix. Sometimes the hard part is actually getting the inverses of the operations. Here's an example for you to practice or to do in preparation for class. I have a nice wholesome looking 2 by 2 matrix, 3, 1, 5, negative 1. Compute the LU factorization of this and use it to solve AX equals B, where B is 1, 0. Of course, only one elementary row operation will be needed here, but it involves fractions. So do this one for class.